Hello everyone. In this video we will learn about Markov chains using different real life examples. So we will learn from theory to practice and we will use multiple real life examples to understand working of Markov chains. So step by step we will cover everything in detail, and here you can see the list of topics that we will cover in this video. First we will start with basic like what are Markov chains, what are states, transition probabilities, what is transition matrix, what are different types of Markov chains like continuous type, discrete type and other, and how we can calculate t-step transition probabilities. This we will try to understand using example, and after this we will solve Markov chain problem. So step by step we will calculate all. And last we have Markov chains limitations, advantages and real life applications. So first we will cover basic. So in this video we will cover basic, and in future videos we will cover advanced topics like hidden Markov models, conditional probabilities, Markov decision processes and all. So step by step we will cover everything. Now let's start it. In simple words, Markov chains are all about states and transition between them. Now, state here is simply the situation you are in right now, and transition is the probability of moving from one state to another. And in Markov chains, the future depends only on the present state, not how you go there. So, this is called memoryless property. So, Markov chains are used to model processes where future depends only on present, not the past. So, this idea is widely used in different areas like in computer science, economics, physics, finance, AI games, and other. So, this is a type of stochastic process characterized by Markov property. Now, what is Markov property? Which is the principle that the future state of processes depends only on its present state. And processes can be written as x0, x1, x2 up to so on. Here, xt is the state at time t. So, stochastic processes are a sequence of random variables written as x0, x0, x1, x2 up to so on. So, what is xt here? It represents the state at time t. T is the time step. Done. So, Markov chains are called memoryless because of Markov property, that is future state. Here it is noted with xt plus 1. It is future state, and this depends only on the current state, that is xt, not on the sequence of past state. We have past state like x0, x1 up to xt minus 1. So here this future state depends only on the current state, not on the sequence of past states, that is x0, x1 up to xt minus 1. And this makes Markov chain memoryless and simple to analyze. Now, what does memoryless means here? Now, let's take a simple example to understand this. Now, just think about playing any board game where dice decide your next move. At any point, your next move depends only on the number you roll on, not the rolls you made early. So, this makes it easy to plan ahead without worrying about entire game history. Same in Markov chains, future depends only on the current state, not on the entire history of how you got there. So, this makes Markov chains simpler to analyze because we need to focus only on the current state. Now, using different examples, we will understand how Markov property work within Markov chains. Markov chain is a sequence of states that process goes through over time, such as x0, x1, x2, where x represent the state at specific time and state at any time t is simply the value of xt. For example, if xt is equal to 5, it means the process is in state 5 at time t. The t is the time and 5 is the state. So, process is in state 5 at time t. Done. What is state space? That is the set of all possible state process can take. For example, here you can see SS state space we have 1, 2, 3, 4 up to 7. Here xt can be 1, 2, 3, 4, 5, 6 or 7. Now next, what is trajectory of Markov chain? Trajectory is like the path that Markov chain follow over time, or we can say the sequence of states the process goes through. For example, if x0 is equal to 1, x1 equal to 5, and x2 is equal to 6, then the trajectory up to t equal to 2 is 1, 5, 6. A time step we have 2. So up to 2 step we have trajectory, that is 1, 5, 6. So Markov property is the core idea behind Markov chains, that is the future state of processes depends only on its current state and not on how the process got this state, means the past history of state like xt minus 1, xt minus 2 up to so on. It does not matter. Now here you can see mathematical expression of Markov property. So Markov property can be written as next state. You can see xt plus 1, it is next state. So next state depends only on current state, that is xt, and you can see xt minus 1 and so on. So the past state do not influence the future state, they do not affect, means past state do not affect the future state, it depends only on the current state. Done. So if sequence of random variable satisfy this property, so we can say that system satisfy the Markov property. Next we have transition matrix. Transition matrix is a way to summarize the probabilities of moving from one state to another state in Markov chains, and this is based on certain transitions. So what is transition matrix? It is a matrix where each entry represents the probability of transitioning from one state to another state in Markov chains. Done. And in this matrix, rows represent the current state and columns represent next state. And Pij is the inserted probabilities. So every entry in this matrix represent the probability of moving from one state to another state, or we can say probability of moving from state represented by row to the state represented by column. Here I, that is the row, j, that is the column. So probability of moving from state I to state j. So here I is the current state, j is the next state. You can see entry Pij located in row I and column j of matrix. It represent conditional probability that system will move to state j. State j is our next state. So the system will move to state j at the next step. Done. Given that system is currently in state I. I is current state, that is now, and xt plus 1, that is our next state represented with j. I means now, j means next. So this is the probability of transition from state I to state j. So initial state means the starting point of process, and states represent the possible conditions, means set of all possible situations the system can be in. And transition probability means probability of moving from one state to another state, and this is represented by transition matrix. Done. Now we will take simple examples to understand states, transitions, and what is transition matrix. So first example we have, now suppose we are tossing a biased coin. So here we have two states, heads and tails, and you can see this is the transition matrix. So if you start with heads, next toss will depends only on current toss, not the previous one. So this creates sequence like heads, 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 tails, heads, tails. For example, we toss the coin and it shows heads. In transition matrix, there is 90% chance that next toss is heads again, and 10% means 0.1, that is 10% chance that it is tails. And second case, if coin shows tails, then there is 50% chance the next toss is tails again, and 50% chance it is head again. Now second example, suppose an online store track customer behavior with three states: browsing, adding to cart, checkout, and exit. Now we have different transition probabilities. Here we have if the customer browsing. Now if the customer is browsing, there is 50% probability that customer will keep browsing, 30% probability that customer will add the item into cart, and 10% probability of checkout, 10% probability exit. Second case, if customer add any item to cart. Now there is 20% probability of browsing, 50% probability he added item into cart, and 20% probability of checkout, and 10% probability of exit. Third case, checkout. Now if customer checkout, there is 100% probability. Now the customer checkout, 0% probability for browsing, cart, and exit. So Markov chains help to understand what customers might do next and by this they can improve their services. Now let's take another example. For example, you are a coffee drinker and every day you decide whether to make coffee at home, buy, or skip. Now, if you make coffee at home today, there is 70% chance you will make again tomorrow. 20% chance you will buy and 10% chance you will skip tomorrow. Done. In second case, if you buy coffee today, then there is 60% chance you buy it again tomorrow and 30% chance you will make it at home tomorrow and 10% chance you will skip it tomorrow. Third case, if you skip coffee today, then there is 30% chance you will skip again and 50% chance you will buy next day and 30% chance you will make coffee at home. So here you can see the transition matrix. 0.7 means 70% chances of making coffee at home. 0.2 means 20% chance when you made coffee at home. The next day it is 20% chances that you will buy outside, and 0.1 means 10% chances you will skip it next day. Done. Like this we have 0.3 means if you buy coffee then next day 30% chance you will make it on. Done. So like this we have all the values. So Markov chains are used to model processes where the future depends only on the present, not on the past. So Markov chains are used to model processes where future depends only on the present, not the past. And in Markov chains, we have different key components. Initial state, that is the starting point of the process. States represent the possible outcomes, and transition probabilities are represented using transition matrix, that is the probability of moving from one state to another state. Now we will take another example to understand states and transition probabilities. Imagine you have a weather app that predict tomorrow's weather based on today weather, and app assume the weather follow certain probabilities. For example, in this example we have three possible states, that is sunny, cloudy, and rainy. Now, if today is sunny, the weather tomorrow has 70% chance of staying sunny. You can see 0.7. This is 70% chance of staying sunny. 20% chance of becoming cloudy. 0.2 means 20% chance of becoming cloudy. 0.1 means 10% chance of becoming rainy. Then you can see this information is summarized in transition matrix. Second case, if today is cloudy, then tomorrow has 50% chance of cloudy. Then 30% chance to be sunny and 20% chance of rainy. And third case, if today is now raining, then we have 60% chance that tomorrow it is rainy, 30% chance of becoming cloudy, and 10% chance of becoming sunny. Then here in transition matrix, each row represent today's weather and each column represent tomorrow's weather. And entry you can see Pij, it gives the probability of transitioning from state I to state J. You can see Pij, here I, that is state I, then state J, that is second state. We are moving from one state to another state. So state I means now, that is the current state. State J, that is the next state. So here row representing current state, column represent next state, and every entry in the matrix represent the probability of moving from state represented by row to the state represented by column. Done. Now next question is how we will calculate the probability for state in Markov chains. So generally we use transition matrix and apply it repeatedly to determine probabilities of each state after certain number of steps. So here first we initialize the state vector that represent the probability for each state. For example, suppose we have three states A, B and C, and if you are 100% sure that you will start at state A, then the initial state vector we have 1, 0, 0. And second case, if you have equal probabilities, means equal chances for states A, B and C, then the initial vector we have 1 by 3, 1 by 3 and 1 by 3. Done. After this we define the transition matrix to show the probabilities of moving between states. For example, in three-state Markov chain, we have three states A, B and C. So row 1 represent the probability of moving from state A to state A, B, and C. And row 2 represent the probability of moving from state B to state A, B, and C. And row 3 represent the probability of moving from state C to state A, B, and C. After this, we will multiply the vector by the transition matrix. Done. Now we will take an example to calculate probability of a state at specific time step. So here we will find out the probability of being in state 2 after step 1 and starting at state 1. So what we are doing here, we are starting at state 1 and we will find the probability of being in state 2 after step 1. So t value we have 1. So after one step we will find the probability of being in state 2. So first we will initialize the vector. So initial state vector p0 we have 1 0 0 and starting state is 1. So 1 0 0. After this we will use transition matrix to calculate p1, that is probabilities after one step. Now we will multiply initial state vector with transition matrix, and after calculation you can see the probability of begin state 2 after one step is 0.3. So p of x1 is equal to s2 value we have 0.3, that is 30%. So right now as we calculated the probability after one step, now what if we want to calculate the probability after multiple steps? Now suppose we want to find out the probability of being in state 3 after two steps and starting at state 2. So our starting state is 2 and we have to find the probability of being in state 3 after two steps. First we will initialize the state vector. So p0 is equal to 0 1 0 because we start at state 2, so we have 0 1 0. Now we will find the transition matrix after two step. So to find out the transition matrix after two step, we will multiply transition matrix with transition matrix and we get this one. Now we will multiply the initial state vector with this result. Now here you can see the probability of being in state 3 after two step is, so like that we can perform multiple steps to find states after two steps or to find states after five steps or multiple steps. So for n step we can use this pn is equal to p naught into t raised power n. Here t, that is the transition matrix raised power n, and p0, that is our initial state vector, and pn, that is the probability of state after n steps. Done. Now third question is how to find out the probability of a chain. Now suppose we have a chain. Now how we will find out the probability of that chain? For example, find the probability of sequence x0 equal to s1, that is state 1, x1 equal to state 2, x2 equal to state 3. So Markov chain is a process x0, x1, x2 up to so on. For example, we have x1, it means process is in state 1, x2 means process is in state 2. Done. So this we will try to understand using another example. Consider Markov chains with three states. So we have three states 1, 2, 3. So this is the state space. We have three states 1, 2 and 3 that has following transition matrix. You can see here P is equal to, we have the transition matrix. Now we have to first draw the transition diagram for this chain. So how we will draw the transition diagram? First we have three states 1, 2, 3. So first draw the circles that will represent our three state 1, 2 and state 3. Now we will use directed arrows between states with the respective probabilities. So probability from state 1 to 1 is 1 by 2. Probability from state 1 to state 2 is 1 by 4. And probability from state 2 to state 1 is 1 by 3. Probability from state 2 to state 3 is 2 by 3. And probability from state 3 to state 2 is 1 by 2. And probability from state 3 to state 1 is 1 by 2. So this is our state transition diagram. Now next task we have given that probability of x1 is equal to 1 is equal to probability of x1 equal to 2 is equal to 1 by 4. So we are given with specific probability distribution at time x1, that is the initial probability, and we are asked to compute a sequence of joint probability over multiple time steps. Here you can see, find out p of x1 equal to 3, comma, x2 equal to 2, comma, x3 equal to 1. So here we will find the joint probability for this, and we have given probability of x1 equal to 1 equal to 1 by 4, and probability of x1 equal to 2 is equal to 1 by 4. Now step by step we will calculate this. So this expression you can see it represent the joint probability of sequence of events in Markov chain. Here x1 equal to 3, it means process start in state 3 at time step 1. x2 equal to 2 means process start in state 2 at time step 2. x3 equal to 1 means at time step 3 process transition to state 1. You can see 1, 2, 3. It is, they represent time steps, and 3, 2, 1. We have three states. First we have initial state probability. So that is the probability that process start in particular state. Px1 equal to 3. You can see here. Next we have transition probability. That is the probability of moving from one state to another that we can obtain from the Markov chain transition matrix. So here you can see, or we have already given initial probabilities. P of x1 equal to 1, 1 by 4. P of x1 equal to 2 is also 1 by 4. Now we will calculate P of x1 equal to 3. Done. And you know the fundamental rule of probability. The sum of probability of all possible outcomes of a random experiment is always equal to 1. So therefore total probability of all possible states must add up to 1. It means the state x1 equal to 1, 2, 3 are the only possibilities. So we have only three possibilities: state 1, state 2, state 3. There is no chance that system is in any other state at time t equal to 1. Done. So total probability must add up to 1. So here we have probability of x1 equal to 1 plus probability of x1 equals to 2 plus probability of x1 equals to 3 is all equal to 1. So this ensures that the system must be in one of three states at any time. P of x1 equal to 2 means probability of being in state 2 at time step 1. V of x1 equal to 3 means probability of being in state 3 at time step 1. So now we will put the values here. So we have already given the values for p of x1 equal to 1 is 1 by 4. Put the value here, and p of x1 equal to 2 is also 1 by 4. We will put the value, and then we have the probability of x1 equal to 3. We have 1 by 2. That is the chances of starting in state 3. We got the value 1. Now we will perform step 2, that is the probability of moving from state 3 to state 2. So as you can see in the transition matrix, the probability of going from state 3 to 2 is 1 by 2. You can see now in step 3, the probability of moving from state 2 to state 1 is equal to 1 by 3. So we are in state 3, then we will move to state 2. After this, we will move to state 1. Now we will multiply probabilities to find out total probability sequence because of the rule of conditional probability in probability theory. Here we want to find out the probability sequence of events. That is p of x1 equal to 3, x2 equal to 2, and x3 equal to 1. So at any time t1, system is in state 3. At any time t equal to 2, system is in state 2. At any time t equal to 3, the system moves to state 1. So we will calculate it using chain rule of probability. So p of x1 equal to 3. This is the probability that system start in state 3. Next you can see the probability that system goes to state 2 given it was in state 3. Done. So why we are multiplying here? Because we are dealing with a sequence of events, and here each step depends on the previous step. Now we'll combine all the terms. So here we will put all the values. So p of x1 equal to 3, we calculated it is 1 by 2, and probability of moving from state 3 to 2 is 1 by 2, and probability of moving from state 2 to 1 is 1 by 3. Multiply all, we obtain 1 by 12. So here we calculated the probability of multiple events happening in sequence. So Markov chains represent a system that transition from one state to another according to specific probabilities and all. So here we cover basic. In upcoming video we will cover advanced topics like hidden Markov models, that is more advanced application of Markov chains. In hidden Markov models, states are not directly visibles. Here we have hidden states. So this is advanced application of Markov chain. Next we have Markov decision process for decision making problems, conditional probabilities, understand the probability of sequence of state and their relationship. So that's all about this video. If you have any questions, you can comment below. And thanks for watching this video.